Welcome back. After topic 1, understanding the basic concepts and variables, and topic 2, learning how to select proper heat equations, you're ready for topic 3, roadmap and solution steps. A. Roadmap for selecting Nusselt number equation. First, you need to confirm that it is an internal flow convection problem and you're looking for Nusselt number. Second, base it upon the heat equation that you selected for the unknown. You need to determine which Nusselt number is desired. Third, if the local Nusselt number is sought, you need to determine the flow pattern. If it is a laminar flow, based upon the thermal boundary condition, you select the proper Nusselt number equation. Otherwise, if it is turbulent flow, for all the thermal boundary conditions, you can select either the Dieters-Boelter Nusselt number equation or the Gini-Linsky Nusselt number equation, where the parameter n is determined by whether the flow temperature is higher or the tube solid surface temperature is higher, and the friction factor F is determined by the Moody chart. Fourth, if the averaged Nusselt number is sought for the thermal boundary condition of constant surface temperature or constant incoming flow temperature, you need to determine the flow pattern. If it is laminar flow, you need to determine whether it is long tube or short tube. If it is long tube, you select this Nusselt number equation, where the average Nusselt number is approximated by the local Nusselt number in the fully developed region. If it is short tube, based upon the Prandtl number range, you select the proper Nusselt number equation. Otherwise, if it is turbulent flow, you need to determine whether it is long tube or short tube. If it is long tube, you select this Nusselt number equation, where the average Nusselt number is approximated by the local Nusselt number in the fully developed region. If it is short tube, you select this Nusselt number equation, where the local Nusselt number in the fully developed region can be represented either by Dieters-Boelter or Gini-Linsky. B. Solution steps. There are 7 specific solution steps for you to follow to solve internal flow convection problem. The best way to learn solution steps is for us to solve the problem together by using it. C. Example 8-3. Apply steps and road map to solve problem. Hot air with mass flow rate m dot enters the circular tube at a flow temperature Tmi and leave the tube at flow temperature Tmo. The tube has length of L, diameter of D. There is convection between the solid surface and a moving fluid. Since the flow temperature is dropping, the surface temperature must less than the flow temperature. We need to determine the uniform surface temperature Ts, which is our thermal boundary condition. Air property is provided. Step 1, this is what we know and what to find out. Step 2, it is confirmed that heat transfer mode is internal flow convection in a circular tube. Step 3, select proper heat equation for unknown Ts. Based upon the thermal boundary condition, we go through the heat equation selection process as shown in previous example 8-2. We select equation 1 to find Ts. Then we plug into numbers TMO, TMI, parameter P pi d, average heat transfer coefficient m dot CPL. From this equation, it is recognized that averaged heat transfer coefficient is desired. Step 4, rest of the work is to follow the 7 specific convection problem solving steps to get average H then Ts. 1. We have identified we're seeking the averaged Nusselt number. 2. We have recognized the thermal boundary condition is constant surface temperature. 3. Air property is given. 4. Determine flow pattern. Equation 2 defines Reynolds number. Then we plug into numbers m dot pi d mu to yield the flow Reynolds number, and then compare with the critical Reynolds number. It is determined the flow is turbulent. 5. Follow roadmap to get Nusselt number equation. Since we're seeking averaged Nusselt number and the flow is turbulent, we compare L over D with 60, and it is determined that the tube is short. Next, we follow the roadmap to get equation 3 for averaged Nusselt number. In this equation, the local Nusselt number in the fully developed region is using teacher's Boiter with n equals 0.3 due to the surface temperature is less than flow temperature. Finally, we plug into numbers into equation 3. Reynolds number, Prandtl number, L over D to yield the average Nusselt number value. 6. Get averaged H. Equation 4 defines the averaged heat transfer coefficient. Plug into number to yield the averaged heat transfer coefficient value. 7. Get unknown. We go back equation 1 and plug into numbers TMO, TMI, P parameter pi d, average heat transfer coefficient, m dot CPL, and solve for the unknown Ts, which is less than flow temperature. This is just to show how to get our Nusselt number equation. We know it is internal flow convection. We're seeking average Nusselt number. The flow is turbulent. The tube is short. Then we got our Nusselt number equation. D. Solution strategy. The solution strategies may help you to organize your thoughts on how to solve internal flow convection problems. 1. If it is a convection problem, you can assume heat transfer coefficient is given. Then select the proper heat equation for unknowns. 2. From the select heat equation, you identify whether the local heat transfer coefficient or the averaged heat transfer coefficient is solved. 3. If the tube length L is not given, you can assume it is a long tube such that the Nusselt number can be evaluated. Then solve the problem and find the tube length. Finally, you verify whether it is a long tube or not. If it is, you stop. If it's not, you treat the problem as a short tube problem, redo it if needed. Let's practice. E. Example 8-4. Apply strategy and roadmap to solve problem. Water with mass flow rate m dot enters the circular tube at flow temperature Tmi and leaving the tube at flow temperature Tmo. The tube has a length of L, inner diameter D1, and outer diameter D2. The tube outer surface is well insulated, and electrical heating within the thick wall provides for a uniform heat flux of Q double prime on the inside surface, which is our thermal boundary condition. There's convection between the solid surface and the moving fluid. We need to find inner surface temperature TSO at the outlet. This is a water property. Step 1. This is what we know and what to find out. Step 2. We need to identify all the heat transfer mode. It is confirmed that heat transfer mode is internal flow convection in the circular tube with electrical heating within the solid wall. Step 3. Select proper heat equation for unknown TSO. Based upon the thermal boundary condition, we go through the heat equation selection process as shown in the previous example 8-2. We select equation 1 to find the inner surface temperature TSO. Next, we plug into numbers, heat flux, TMO, and we recognize that the local heat transfer coefficient is desired. Step 4, rest of work is to follow the 7 specific convection problem-solving steps to get H at x equal L and then TSO. 1. We have identified the local Nusselt number is desired. 2. We have recognized the constant heat flux thermal boundary condition. 3. Water property is given. 4. Determine flow pattern. Equation 2 defines Reynolds number. Then we plug into numbers m dot pi d mu to yield flow Reynolds number, and then compare with the critical Reynolds number. It is determined the flow is laminar. 5. Get Nusselt number equation by following roadmap, which is equation number 3. 6. Get local H value. Equation 4 defines the local heat transfer coefficient. Then we plug into numbers to yield the local heat transfer coefficient value. 7. Get unknown. We go back to equation 1 and plug into numbers, heat flux, local heat transfer coefficient, TMO, solve for TSO, which is greater than the flow temperature. This is just to show how we get the Nusselt number equation. It is internal flow convection. We're seeking local Nusselt number. The flow is a laminar. The thermal boundary condition is constant heat flux. And this is what we select, Nusselt number equation. At this point, we covered topic 3, roadmap and solution steps. We tackled the challenge on how to select heat equation through the examples. See you next time.